Welcome back. In this lecture we will conclude the existence and uniqueness of the Brouwer local Brouwer degree. So let me just formulate our main results. So this is exactly the theorem. Let's call it existence and uniqueness of local Brouwer degree. And let's begin. Just simply say there exists a unique function which we denote degree z, satisfying the properties So remember, this was P1, it was additivity, P2, it was homotopy, and P3, it was normalization. Well, maybe that's it, just this property, and in such a case that actually proves the existence of the degree, because the degree was defined as a function satisfying exactly these three properties. So let's start the proof, and we will show that in fact such a function exists, and for that purpose we need to define it. So let f and omega belongs to M, so this is the collection of all admissible pairs. That means simply that f is a continuous map from V to V, a Euclidean space. So that's continuous map, and we have here omega contained in V, that is an open bounded set, and here we have here that f is admissible, f of x is not equal to 0 for every x belonging to the boundary of omega. So by Sartre theorem, there exists by Sartre and Weierstrass theorems. We already discussed it in the earlier lectures. There exists a regular map, there exists a C infinity map, call this one f in tilde from V to V, such that and here we have here two properties, A that 0 is a regular value of f tilde in omega, and b is that, let's write it down, supremum for x belonging to omega, and I say closure, and that will be f of x minus f tilde of x is smaller than, this is infimum, this is x belongs to omega, and that one is f of x. And we already talk about this condition, that this condition is basically guaranteeing that if we call that value epsilon, so this epsilon approximation f tilde is in this case an admissible, omega admissible map. So in certain way we can say that in such a case, so f tilde omega is an admissible pair and moreover f tilde is homotopic to, just by linear homotopic to f by an admissible, omega admissible homotopy. So maybe let me just recall that such a map with these two conditions, so in such a case we'll call that this is a regular map in omega. So that means this is a regular map in omega. And that of course allows us to let's say conclude. So since the set, and I put here f tilde minus 1 of 0 intersection omega is finite, so let's write it down. This will be like x1 xn, so is finite, maybe we don't need it, the bracket, is finite and composed of regular points of f, f tilde, we can write, and this is our definition of the local Brouwer degree, we can just simply write that this degree f of omega will be by definition equal to the sum, and here we use the approximation, so x belongs to f tilde minus 1 of 0 intersection omega, and this is signum, omega is added omega, and this one is signum determinant d, and this is f tilde of x, and that's our formula 1 that will use the definition. So now we need to show, first one, fact number 1, the formula one does not depend on the choice depend on the choice of a regular approximation f tilde. And indeed, so suppose here we have two approximations. So suppose here, indeed, suppose we have two such regular approximations, and let's write it down. This is f omega, and we know this pair will be homotopy by omega admissible homotopy to a certain first approximation f1 of omega, and it is also homotopy to another one. So that's what we have it. So now, as you see, homotopy is a transitive relation that implies, so maybe you should put it like this, therefore f1 omega is homotopic to f2 tilde omega. That means it satisfies the assumptions of lemma 3, therefore, and, put it clearly, by lemma 3 from last lectures, from lecture number 3, we have, and that's the formula, sigma x is in f minus 1 0 omega, and then we have here signum determinant, this is df tilde 1 of x, and that is equal again sigma, put here x prime belong to the f tilde 1, sorry, f tilde 2 minus 1 of 0 omega, signum determinant d f tilde 2 x prime, I call this formula 2, so, which implies that the both approximations f1 tilde and f2 tilde give us the same integer, which is exactly deg f omega. So that means it does not depend on the approximation. Notice that what we have here in this diagram is actually little more. Namely, notice, so this is fact number 2. Notice that exactly the same argument can be applied to prove the property P2, namely namely, suppose we have here two maps. Suppose I have here F1 omega, which is homotopic, admissibly homotopic with F2 omega. So how do we compute the degree? We just take the approximations, regular approximation F tilde omega, and here we take the approximations of F2 tilde omega, and that gives us a homotopy between these two approximations. This is homotopy here. That one is approximating homotopy. This is approximating homotopy again. And then that one is the homotopy that results by transitivity of the homotopy relation. We are getting that these two approximations of F1 and F2 are homotopic, admissibly, omega admissibly. Therefore, we can apply again lemma 3 and the formula. And the formula 2 that we just obtained here, this formula, that one, this is our formula. So this is our formula. This formula gives us that the degree of F1 omega is equal to the degree F2 omega. F2 omega. So the property number 2 is satisfied. Notice fact number 3. The property P3 is obvious. So what is the property P3? That means, suppose here that we have here an x naught, and this x naught does not belong to the boundary of omega, does not belong, so we have that the degree of identity minus x naught on omega is equal 1 if x naught belongs to omega, and 0 if x naught is not belonging to omega. So indeed, put f of x is equal x minus x0. So you can see immediately that f of minus 1 of 0 is exactly x naught, and df of x naught is equal to identity. So signum determinant of df of x naught is equal to 1. And therefore we have two possibilities. So we have here possibility number 1, that if you take the identity minus x naught omega, so you have here that in this case this must be 0 if x naught doesn't belong to omega, because f minus 1 is 0 intersection omega is empty, so there is nothing to sum up. And this must be 1 if x naught belongs to omega, then f minus 1 of 0 omega is equal to x naught, so the signum determinant is equal to 1. Equals. And that is done. So the only one that is left is basically fact number 4. the formula, the degree, the function degree from m to z defined by the formula 1 satisfies the property P1. To be more precise, indeed, let f minus 1 of 0 intersection omega, so we are still talking about admissible pair f omega, is contained in omega 1 union omega 2, so those are two subsets of omega, and they are disjoint, so this means this is equal to empty set. So in such a case, we have situation that zeros are, so you see this is my omega, this is my omega, and zeros are either in omega 1 or omega 2. So those are the 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, zeros. So let's do it. So we'll show that this is indeed, the property is satisfied. So what I'm going to do is, now let me simply define the number epsilon. So let me say epsilon, okay, is by the definition it will be infimum for x belonging to omega bar minus omega 1 union omega 2, and this will be f of x. So that number, you see, this is infimum over that set. There are no zeros here, so that number, by compactness of the set here, of this set, is not zero, and that means it's positive. So this is positive, this is compact. So f is continuous, so such a number is definitely positive. So we can use it as the approximation. So by Sartre theorem, okay, maybe I call it like this, by regular approximation theorem, there exists a map f tilde from V to V such that, and then we have here A, f tilde is C infinity and 0 is a regular value of f tilde restricted to omega, and B is that's approximation, that for every x belonging to omega bar, we have here f tilde of x minus f of x is smaller than epsilon. So that's epsilon approximation. So that's it. So in such a case, what do I obtain? So by this condition, call this condition 3, by 3, we have that f tilde minus 1 of 0 intersection with omega must be contained in either omega 1 or omega 2. So we have that we can write it down. So we have those degree of f on omega will be equal, and let's write it down. This will be the same as for the approximation. So if I feel like this, x belongs, by the definition, x belongs to the f tilde minus 1 of 0 omega, and this will be signum determinant derivative of f tilde of x, and that one is equal to sigma, and this is x belongs to f tilde minus 1 of 0 omega 1 signum determinant df tilde x plus, and this is another sigma, this is x belongs to f tilde minus 1 0 omega 2, by that property here, by this property, and then we have again signum determinant df of x, but that guy here, this guy here, is nothing else than the degree, by the approximation, by definition of the degree. This is degree of f in omega 1, and the second one is degree of f in omega 2, and we prove the additivity properties. So notice, fact number 5, notice that the uniqueness of the degree follows from the analytic formula for degree. So trivially, so it's clearly that it cannot be other number than the number that we specify. And that's the end of our proof. So next we should concentrate on some additional properties of the degree, of the local Brouwer degree. So let's formulate it as a kind of the heading, additional properties of degree, just simply degree, underline, and let's start. Proposition. Suppose. So let's say like this. Maybe write it down. The degree, which we know exists as unique, degree from n to z has the following property, So this is our property. I call this property P8, and we'll call it product property. Product. So let's formulate it. Let, if you f omega and another pair g u both belong to m, so those are two admissible functions, then we have here the degree of the product of these two maps on the set omega times u will be the product of degrees of integers. So let's do the proof. Since the degree of f and its approximation, its regular approximation, is exactly the same, so let's simply assume, without loss of generality, that f is regular and so in omega, and G is regular in U. So that means they are both C infinity. That means in particular, that means C infinity and zero reg value. The same here. C infinity, zero reg value. And that implies in particular, so we have here that f times G is also regular in omega times U, and we have notice this is f times G and minus 1 over 0 intersection omega times U. So this will be nothing else than f minus 1 over 0 intersection omega times Cartesian product G minus 1 over 0 times U. And for every, put it like this, x, y belonging to this set, f times G minus 1 over 0, intersection omega times U, that's what you're interested, we have that, and it looks like this. So here, we have here the derivative of f times G, and this point x and y will be a block matrix that looks like this. This is Tf of x standing here. This will be Dg of y standing here. There will be 0, there will be 0. And that's the derivative. So, you can notice that this determinant will be the product of determinants. So here, determinant of G of x. And then we can just simply write. So, therefore, we get and then write it down. Degree, this is f times G, this is omega times U is equal, and this will be sum, this will be x and y belongs to the f times G minus 1, 0 intersection omega times U, and this will be the signal determinant of df times G at x and y, and then we can rewrite it now as that one, so I write it down. This is x belongs to the f minus 1 of 0 omega. Second sigma is y belongs to g minus, sorry, y belongs to the g minus 1 of 0 u, and then the signum, use the fact that the determinant is a product of determinants, that this will be signum determinant of df of x times signum determinant of dg of x, and then you can just simply split it into the two product of two sums. This is a signum determinant of df of x times, and you can write the second one, y, this is of course y, belongs to g minus 1 of 0 u, and this will be signum determinant dg of y, and according to our definition, by our definition 1, so this will be nothing else to the degree of f in omega times to the degree of g on u, and the product formula is proved. So the next property is kind of important, and this property, which is also known as the Borsuk theorem, requires additional lemma. I'm not going to prove this lemma now. Later on we will be proving this formula for much in a more general case. This is exactly here a case of the equivariance, when we have here a simplest non-trivial group Z2 composed of 1 and minus 1, and this group acts on the space by antipodal action, that means by multiplication by minus 1, and we are dealing here with the map that is equivariant. In our case we'll call it odd. So I am going to prove this theorem later for any compact Lie group. Therefore, we in a moment accept this lemma without proof, and we will postpone the proof for the appropriate moment. So let's begin with lemma. And so call this odd approximation. Lemma. Sorry, odd, maybe write it down. Regular. Use it, let's use it. Red color is always good to emphasize. So odd, regular approximation. Lemma. So assume that we have a omega contained in V is an open, bounded neighborhood of 0 such that minus omega is equal to omega. We say, so that means we call such a case omega is symmetric. Is symmetric with respect to 0. So this is symmetric. But maybe it's also appropriate to say, or you can say also Z2 symmetric, Z2 symmetric. But that's the condition. This is the condition. Minus omega is equal to omega. 10 for every epsilon and every admissible pair omega n such that f is odd, and that will mean the following, that f of minus x is equal to minus f of x, and this is for x belonging to V, and there exists an omega admissible regular f tilde such that maybe in omega regular admissible regular omega map f tilde such that A, this is still odd, and B, that supremum x belongs to omega bar f of x minus f tilde of x smaller than epsilon. So that means this is epsilon approximation of the f. The epsilon approximation of the f. So now we can formulate the main result, which is called the Borsuk theorem. Borsuk theorem. So let's say like this: theorem. Let omega contained in V be an open bounded symmetric or Z2 symmetric. So let's say like this is Z2 symmetric set. So maybe I should explain omega is equal to minus omega set, and f from V to V be an omega admissible map such that for every x belonging to boundary on omega, so f of minus x is equal minus f of x. So that means the map is not necessarily odd. The map is only odd on the boundary, and the boundary is symmetric, so it makes all the sense. So we have here the statement 10, for an odd map we're getting odd degree 10, the degree f omega is an odd integer. And we just do the proof quickly. So let's say like this, the f is not odd, we replace it by odd. So defined. And I put here f1 going from v to v by the formula that means f1 of x is equal, and this will be 1/2, and here I put here f of x minus, this is f of minus x. Let me put it dark because it is sweaty. And this is for all x belonging to v. So you can notice, as an immediate consequence of the definition, that f1 is odd, so call it like a bullet and another bullet, and f1 of x actually is equal to f of x for x's belonging to boundary of omega. So these two conditions are easy to verify. Anyone can do it easily. So now, once we have here 10 by boundary, call it like this, value property of degree, which was the property, I think, P7, we have that the degree of f of omega is equal to the degree of f1 on omega. So that is done. So now we can just simply work on the map f1. However, by lemma, there exists an odd omega admissible map, admissible regular map. Call this map f tilde, like in the lemma, from v to v, such that this is an appropriate approximation of f1. So what will be the approximation? Supremum, and this is x belonging to omega, and then I have here f1 of x minus f tilde of x must be smaller strictly than infimum. By the way, you should understand that by compactness of omega bar and the boundary of omega is also compact, those will be maximum and infimum. So this is x is actually infimum, is replaced by minimum. So but for convenience we just keep writing infimum. So remember it, this will be always, this is more, they can be replaced by max, and this will be minimum. So we have here, and that's a condition that will guarantee that your approximations are also omega admissible. And now an odd, so since f tilde is odd, we have immediately that f tilde of 0 must be equal to 0. Indeed. Okay, let's see. So f tilde of 0 is equal f tilde of minus 0. It is equal by oddness f tilde of 0, and this implies that 2f tilde of 0 is equal to 0. So that's how we show it. It must be 0. So in such a case, it is exactly 0. So therefore, so we have here that, and maybe this, maybe put it like this. And if x naught belongs to omega is such that, okay, if maybe write it like, if x naught belongs to the f tilde minus 1 of 0 omega, then minus x naught also belongs to f tilde minus 1 of 0 omega. Indeed. If you have here f tilde of minus x naught, this is the same as minus f tilde of x naught, but since this is 0, so you are getting this is 0. That's it. Thus, therefore, we have the following composition of the zeros in omega, namely it is equal. 0 is there, and then you have finitely many points, and they all appear in pairs. You have here first point, which is x1, and minus x1. Then you have here x2 and minus x2. And finally, xm and minus xm. So this is the composition. So now, also notice that since minus f of minus x tilde is equal to the f of x tilde, we have, by the chain rule, that minus df tilde minus x composed with minus identity is equal to the df tilde of x, which implies that df tilde of minus x is equal to the df tilde of x. So we have, and let's write it down, degree of f omega is equal to the degree of f tilde omega, and this one is equal to the sum, and this is x belonging to f tilde minus 1 of 0 omega, and this is signum determinant df tilde of x. And now we look, we know exactly what this set is looking like. So this is here. So this set looks exactly as that one is equal, so we can write it down. This is the signum determinant of df tilde at 0, and then plus, and then you have here signum, and this is k is equal 1 to n, signum determinant of df tilde of xk, and this is plus, because they both appear in the pair, so this is plus signum determinant of df tilde minus xk. But that implies simply that this is signum determinant df of 0 plus, and that one is 2 times k is equal 1 to n, and this will be signum determinant df tilde of xk. Since for any signum determinant, since signum determinant is either signum determinant of df tilde of any x naught this is a regular point, so that means xk, for example, is equal plus minus 1. We are getting here that this is equal plus minus 1 plus 2 certain value. Let's call this value n. So that is an odd number. And the statement is proved. So statement is proved. So we have this theorem. So let's use this theorem to prove kind of a nice result, and it is a well-known result in analysis, and even that's actually topological result that is interesting to know its proof. So maybe change the paper and let's write it in another result, so call it proposition. Proposition, and this is called the invariance domain theorem. Domain theorem. Invariance domain theorem. So let's start. Let U, which is subset of V, remember V is our Euclidean space Rn, be an open set, not necessarily bounded, and F that goes from U to V, and injective and continuous map. Then we have, and put here like this, A, that F of U is open in V, and B, inverse map, which is well defined, F minus 1 from F of U, which is open to U, is a homomorphism. Is continuous, maybe. Is continuous is better. Is continuous. And that means in particular that F from U to F of U is a homomorphism. And you have, this is homomorphism. Okay, let's prove this theorem. So proof. So remember, we need to prove two things. We need to show that F of U is open and F minus 1 from F of U to V to U to V is continuous. So what does it mean? So let me do the following. Suppose that we have here F of x naught is equal to y naught, and in such a case we will show that for every delta larger or than 0, if we know that B delta of x naught is contained in U. So we have here closed ball, closed neighborhood of x0. So for this delta there exists an epsilon larger than 0 such that here epsilon ball of y0 is contained in f of B delta x0. So notice that this condition, call this condition, maybe I put it here, call this star. So notice that star implies both that A and B is satisfied. Implies that f of U is open. Why? Because just look here. A neighborhood of, let's say, the image of a neighborhood of x naught contains a neighborhood of f of x naught. So that means here it's clearly open. So this condition implies that this is an open set, that U is an open set. And maybe let me show it clearly. So here we have here x naught. So this one is going here to y naught. So this is your f, and this is your U, f of U, and then you have your small neighborhood here, which is contained in the f of B delta of x naught, which must be also in f of U. So maybe write it here, because we have here that B epsilon y naught contained in f of B delta x naught, and that one is contained in f of U. Okay, so that means it's open. On the other hand, in particular, and since we also have for every delta larger than 0, satisfying the condition that of course B delta x0 contained in U, there exists epsilon larger than 0 such that we have here epsilon y0 is contained in f B delta of x0. That one is equivalent to say that f minus 1 of B epsilon of y0 is contained in B delta x naught, but that one is equivalent that if y minus y0 is smaller than epsilon, then this will imply that f minus 1 of y, so sorry, I don't use doubles, I use single absolute value for the norm. Y minus y0 smaller than epsilon implies that f minus 1 of y minus f minus 1 of y0 is smaller than delta. So this is the continuity of f minus 1. So what do we need to show? We just need to show star. Therefore, we need to show star. We need to show star. So assume. So first of all, choose this x naught belonging to omega and fix them. And and put y naught is equal f of x naught. Sorry, no, this is not omega, this is u. This one is u. This one is u. And y naught is equal f of x. Since here we are doing continuity, so what about shifting? By changing coordinates, by shifting coordinates in domain and image or codomain, we can assume, again without losing generality, that these two fixed points, that x naught is equal y naught is equal to 0. So that means f of 0 is equal to 0. So that means by changing the positions of these points, the coordinate systems, by moving the coordinate system in the domain to x naught, the center of the coordinate system to x naught, and by shifting it in the codomain to y naught, we are getting this situation. So choose, so let delta larger than 0 be such that, and I put here omega, which is equal to b delta x 0, is contained, then we make sure this is contained in the closure, and that one is still contained in U, so we still have a situation with the U. So this is U. And I have this omega. So next thing, define the homotopy. So we define the homotopy, and this homotopy will be defined on the 0, 1, and times omega bar. Notice that anything that is defined on the closed set in the metric space can be continuously extended to the whole space by theta extension theorem. So in our case, I can just simply restrict myself to the values of this homotopy on the omega bar, and this will go to V by the formula, and the formula is this one. So this will be H, and it will be Tx by the definition is equal F, and I put here X divided 1 plus T, and this will be minus F, and this will be equal to minus Tx 1 plus T. So here X of course belongs to the omega bar, T belongs to the 0, 1. So notice, first one, put here a bullet, that H0 of X, this means when T is equal to 0, is equal F of X, and this one is equal to 1 plus 0, this is minus, and this will be F, and this is minus 0x 1 plus 0. So you can immediately recognize that this is equal F of X minus F of 0, which was 0, so this is equal F of X. So you are getting this one. And the second bullet is that H1 of X is equal, this is F, and this will be X divided by 1 plus 1 is 2, minus F of minus X divided by 2. So H1 is an odd map. It's an odd map. We claim, I claim H is an omega admissible homotopy. Indeed, assume that for some t and x belonging to 0, 1 times omega bar, we have 0 is equal to h of t x, and that one, of course, by the definition will be equal to x 1 plus t minus f, and this will be minus t x divided by 1 plus t. This is kind of a mess. 1 plus t. And that, of course, is equivalent to say that f of x 1 plus t must be equal to f of minus tx 1 plus x, t. Since f is injective, so that means these two values equal if and only if these 2 points are equal. We have that in such a case x 1 plus t must be equal to minus tx 1 plus t, 1 plus t, and that one you can rewrite it down that this is the same as x must be equal to minus tx, and that one is that 1 plus tx is equal to 0, so we are obtaining that x is equal to 0, and that means it is not having, that h is not having any zeros on the boundary. The only zeros possible is in the center. H goes in the center, so that's what we get. So we have it. So now, of course, once we have it, so what do I get here? By admissibility, of the homotopy, by admissibility of the homotopy H, we obtain, and let me write it, that the degree of our f, which is original map on omega, is the same as the degree of H1 on omega. Here. This is the first property. That one is equal to 0. And the second one is odd map. And that implies that this one is equal to odd integer. But the nice thing about odd integers, they are not equal to 0. So therefore, degree of f on omega is not equal to 0. So now, take epsilon, which is equal infimum, and this is x belongs to the boundary of omega of f of x. We know that this infimum must be positive, and consider, maybe not nice, the map And I will denote this map like this. F of y of x is equal f of x minus y. Minus y. So, if the norm of this y is smaller than epsilon, then we are getting here that fy of x minus f of x is exactly equal to y, and that one is smaller than epsilon, which implies that fy is omega admissible. Moreover, actually, we can put here little t as a homotopy, so this will be t added here, so this will be t. So maybe I put here like that, t, f of t. Maybe I should not mess up. How should I should just rewrite it correctly. So in particular and in particular we can use the homotopy. So I put here like this, h tilde tx, which is equal to f of x minus tx. So we are getting here that h tilde 0 is equal to f of x, and h tilde 1 is equal to fy of x. Yeah. And this homotopy will be admissible. Clearly, it is still satisfying this property. And what do I get here? I'm getting here that so degree of f on omega is equal to the degree of fy on omega, which is equal non-zero. 10 by existence property, which is which one? Which is P4. P4, we have, since this degree is non-zero, we have here that there exists an x belonging to omega such that fy of x is equal to 0, but this is equivalent that f of x minus y is equal to 0, and this one is equivalent to say that in such a case f of x is equal to y. So that is, and therefore, because this is true for every y, since this is true, since this is true for every y belonging to the b epsilon 0, we have that b epsilon 0 is contained in f of omega, which let me remind, this is b delta of 0. So that was actually proving by 10 again, by returning to the original coordinates. We have that b delta y0 is contained in f of b, not delta, epsilon y0 is contained in f of b delta of x naught. And that's the end of the proof. Let's prove it. So I think this is enough for this lecture, and we will continue with the properties, additional properties of the local Brouwer degree next time. We also show a couple of simple applications of this degree to make some interesting observations about the functions and the properties in the elementary finite dimensional cases. Thank you, and that will be enough.